5 miles off the Kona coast, there is no dock and no shoreline visible in any direction. There is only open ocean, a surface buoy, and a mooring line running down toward a steel cage submerged 40 feet below. Hawaii's industrial aquaculture does not operate from a beach. It operates from a depth. Most of its infrastructure is invisible, running beneath the surface, moored in cold water and pumping continuously. Hawaii's offshore aquaculture system draws cold seawater from depths exceeding 2,000 feet to sustain commercial fish production in open ocean conditions. This video traces the full system from deepwater pipe to processing dock. If this level of operational detail is worth following, subscribe and leave a like below. Tell us in the comments, did you know open ocean cage aquaculture was operating in Hawaii? The cold water pump at NELHA has already been running since before sunrise. The Natural Energy Laboratory of Hawaii Authority, NELHA, sits on the western coast of the Big Island, built on lava rock at the edge of the Pacific. Since the 1970s, it has operated one of the few commercial deep seawater pipeline systems in the world. The NELHA pipeline draws cold seawater from a depth of 2,200 feet, where temperature holds between 6 and 8 degrees Celsius year-round. That temperature differential between the deep draw and the warm surface ocean is the engineering foundation of the aquaculture systems built around it. Three pipeline systems run from the deep ocean to the surface facility, one drawing warm surface water and two drawing cold water from depth. Together, they deliver over 27,000 gallons per minute to the campus, where aquaculture tenants pay for metered access. Aquaculture tenants at NELHA lease cold water access for their holding and hatchery systems. The water arrives naturally low in pathogens and elevated in nutrients carried up from depth. It is not treated with chlorine before entering production tanks. Fingerling production begins inside enclosed hatchery buildings, where juvenile fish are held at controlled densities in temperature-regulated tanks. Water exchange rates are calibrated daily, and at this stage, the fish are measured in centimeters, not kilograms. The primary species in Hawaii's offshore cage system is the almaco jack, marketed commercially as Kona Kampachi. It is a fast-growing pelagic species adapted to warm, high-oxygen offshore conditions, and the combination of shore-based cold water infrastructure and open ocean cages gives it consistent grow-out conditions through the full production cycle. When juveniles reach transfer size, typically 50 to 80 grams, they are loaded into aerated transport tanks mounted on flatbed trucks. The drive from the NELHA hatchery to the harbor takes under 30 minutes, with tank temperature monitored throughout. At Kona Harbor, a work vessel receives the incoming fish using a pump and tube transfer system from the truck containers into aerated holding boxes on deck. Once loading is complete, the vessel departs on a fixed heading toward the cage mooring 5 miles offshore. The open ocean cage is moored on a taut-line system that holds position against Pacific current and swell, not anchored in shallow coastal water. The cage frame is a submersible steel structure approximately 20 meters in diameter with a high-density polyethylene net suspended inside. The submersible cage design allows it to descend below surface wave action during storm events, with ballast tanks in the frame controlling buoyancy and operating depth. In normal conditions, the cage sits between 15 and 40 feet below the surface. Fingerlings are introduced through a transfer tube connecting the vessel to the cage collar, with a counting system on deck recording fish per batch transferred. Stocking density inside the cage follows limits set by both the state of Hawaii and federal offshore aquaculture permitting. Feeding begins immediately after stocking, with pelleted feed pushed through a pneumatic blower system from the vessel into the cage feeding zone. Feed conversion ratios are logged from the first day of each grow-out cycle. Grow-out takes approximately 10 to 14 months under Hawaii's offshore conditions. Surface water temperature averages 26 degrees Celsius through most of the year, providing thermal consistency that supports continuous growth without the seasonal slowdowns common in temperate aquaculture systems. Monitoring at the cage site runs weekly, with technicians conducting underwater inspections to assess net integrity and fish behavior. Cameras mounted inside the cage transmit footage to a shore station where feed response and fish condition are tracked remotely. Biofouling, Marine organism accumulation on net surfaces reduces water exchange through the cage if unmanaged. Net panels are cleaned on a rotating schedule, and in heavy fouling periods they are removed, towed to harbor, and high-pressure washed before reinstallation. Water quality sampling at the cage site is conducted monthly. We're measuring dissolved oxygen, temperature, salinity, and current velocity at multiple depths around the cage perimeter. Dissolved oxygen below a critical threshold triggers an immediate reduction in feeding rate to lower biological load inside the cage. Feed deliveries run on a schedule tied to vessel fuel budget and harbor operations, requiring bulk feed bags loaded at the dock warehouse, transported offshore, and delivered through the blower system within each feeding window. This cycle repeats throughout the grow-out period without exception. At approximately 12 months, fish approach target harvest weight, between 3 and 5 kilograms live weight. A dip net sample is drawn from the cage and weighed on deck, and when the average consistently hits target, harvest planning begins. Harvest is scheduled to align with processing plant capacity, cold chain availability, and air freight departure windows from Kona Airport. A missed freight slot means holding fish an additional day, increasing feed cost and handling risk. On harvest day, a larger work vessel carries a deck crew of 4 to 6 and moors at the cage collar. A crowding net inside the cage is drawn toward the harvest side, concentrating fish into a reduced volume of water before lifting begins. A braille net is lowered to lift fish from the crowded zone in batches, with each lift bringing up several hundred kilograms. Some fish are transferred directly into a slurry tank on deck, a container filled with seawater and crushed ice. The slurry tank drops fish body temperature within minutes of harvest, a process called thermal stunning that reduces struggling, prevents bruising, and starts the cold chain at the point of capture. Tank temperature is held at 0 to 2 degrees Celsius throughout the operation. On deck, crew sorts fish by weight class using a portable scale, returning undersized fish to the cage. Accepted fish are packed into insulated foam boxes in alternating layers of fish and ice, then sealed and labeled for processing. Total harvest from a single cage cycle ranges from 50,000 to 150,000 pounds of live weight, depending on stocking density and cumulative mortality across the grow-out period. Yield per cage is calculated against total feed input and operating costs to determine batch performance. The harvest vessel returns to Kona Harbor, where foam boxes are offloaded onto rolling dock carts. A refrigerated van receives the product at dockside, and transit from harbor to the processing facility is under 15 minutes. The processing facility runs 2 shifts during harvest weeks, with the early shift beginning at 4 a.m. to handle incoming product and meet outbound air freight windows. The plant is HACCP certified and subject to routine inspection under Hawaii Department of Agriculture protocols. At the receiving dock, each incoming box is weighed, logged, and temperature checked before proceeding. No fish enters the production line without a temperature record on file, and the cold room receiving area is held at 1 degree Celsius. Processing begins with bleed and chill. Each fish dispatched and bled over a trough running with cold water. Bleeding is completed within 2 hours of harvest landing to preserve flesh quality and extend shelf life. At the filleting station, operators run cuts along the spine of each fish to produce 2 fillets. Average yield is 45 to 50% of live weight per fish, depending on the size class entering the line. Each fillet passes individually under a UV light inspection table to detect parasites or defects. Any fillet that fails is diverted, logged, and directed to a secondary product stream for cooked or value-added applications. Accepted fillets continue forward on the line. Accepted fillets move to the trim and portion station, where operators follow cut specification sheets tied to customer orders. Restaurant accounts receive skin-on fillets within precise gram ranges. Retail accounts receive skinless vacuum portions at a uniform cut size, while portions outside the specified weight window are returned for trimming or redirected. The production target is 95% of output within specification per shift, and supervisors monitor line accuracy throughout using inline scale data. After portioning, product enters the vacuum packaging station, where bags are machine sealed and labeled with lot number, harvest date, species, and facility code. Every packaged unit is traceable to the cage site, the harvest date, and the processing batch. Those packaged units are placed into master cartons with gel packs, sealed and moved into the cold room at -1 degree Celsius. This is the final hold point before transport to the air cargo terminal at Kona Airport. Kona Airport is 15 minutes from the facility by road, and refrigerated vans run timed trips to the cargo terminal during freight windows. Product for the continental U.S. loads onto next available commercial cargo departures from Kona daily. Some Pacific Rim markets, primarily Japan, receive shipments on a twice-weekly schedule via Honolulu International, with product transferring from Kona by inter-island cargo flight before connecting to trans-Pacific freight. Total cold chain time from harvest to Tokyo is under 36 hours. On the U.S. mainland, product reaches wholesale cold rooms in Los Angeles, San Francisco, and Seattle within 24 hours of leaving Kona. Restaurant buyers hold standing weekly orders, and a portion of product reaches premium retail grocery display on the West Coast. Between harvest cycles, the operations team at NELHA conducts scheduled maintenance reviews, pipelines inspected quarterly, pump stations serviced on rotation, hatchery tanks cleaned and sterilized. Preparation for the next juvenile cohort begins before the previous cycle's records are fully closed. After each production cycle, the cage net is removed and towed to harbor for inspection and cleaning. The mooring site rests 30 to 60 days between cycles to allow seabed conditions below the cage footprint to recover. The permitting structure for Hawaii's offshore aquaculture involves both federal and state regulatory layers. Federal permits under the Magnuson-Stevens Act govern open ocean operations, while state permits cover water use, facility operations, and environmental monitoring requirements at NELHA. Environmental monitoring is a condition of both permit sets, with quarterly seafloor surveys documenting benthic community composition at and around the cage site. Survey data is submitted to NOAA in the state as part of annual compliance reporting. The cold water infrastructure at NELHA supports more than finfish aquaculture. Other campus tenants operate shrimp nurseries, microalgae cultivation systems, and sea cucumber conditioning facilities, all drawing from the same shared deepwater pipeline network. Energy cost is among the primary operating expenses for the deepwater pipe system, as pumping from 2,200 feet requires continuous electrical load. Some NELHA tenants have explored ocean thermal energy conversion, OTEC, as a method of generating electricity from the temperature differential the pipeline already exploits. The workforce operating Hawaii's offshore aquaculture system is small relative to the infrastructure it manages, typically 8 to 12 full-time employees across hatchery, vessel, and processing roles. Harvest periods bring in additional contract labor for packing and cold room operations. Scale limitations remain significant. Hawaii's offshore aquaculture output represents a fraction of the state's seafood consumption, and most seafood eaten in Hawaii is imported. The existing cage operations demonstrate technical and regulatory viability, but have not yet expanded to volumes comparable to Atlantic salmon or commercial shrimp aquaculture sectors. The infrastructure, however, is established and operational. The cold water pipe runs. The permit framework is tested and documented. So the cold chain from offshore cage to international export market is repeatable and on record, a working model of depth-supported open ocean fish production. The last box is sealed. The refrigerated van departs the dock. The vessel waits at harbor for the next feed run, and 5 miles offshore the cage holds the next cohort. The cold water pipe draws from 2,200 feet, sustaining a production cycle that does not pause. Under this video, there's a subscribe button. It's a small action, but it helps document how water becomes food at scale. If you found this system worth following, leave a like. And tell us, where are you watching from? Have you ever worked in aquaculture or seafood processing?